Do you ever wonder what causes those breathtaking light shows in the sky we call auroras? The answer lies in an incredible cosmic dance between the Sun and Earth's magnetic field. Today we're diving into the stellar relationship that shapes our space environment and creates some of nature's most spectacular light shows. Let's start at the source, our Sun, and work our way back out. The Sun isn't just a uniform ball of fire. The Sun has distinct layers, each with unique properties that contribute to its dynamic behavior. At the core, temperatures reach 27 million degrees Fahrenheit. This extreme heat and pressure allow nuclear fusion to occur, where hydrogen atoms combine to form helium, releasing enormous amounts of energy. This energy is what powers everything in our solar system. Someday we may be able to create our own fusion reaction here on Earth, but for now, this is all we've got. Surrounding the core is the radiative zone, where energy slowly travels outward via radiation. This zone is so dense, it can take a photon or particle of light up to 170,000 years to pass through it. Next comes the convective zone. Here, the plasma becomes less dense, allowing convection currents to form. Hot plasma rises to the surface, cools, and then sinks back down, similar to water boiling in a pot. These churning movements generate powerful magnetic fields that extend throughout the Sun. The top layer of the convective zone we see is called the photosphere, with a temperature of about 10,000 degrees Fahrenheit. This is the part we can see most clearly. The splotchiness that you see is the result of granules or supergranules depending on size that can be seen on the surface as bright and dark spots for upwards and downward currents. This is also where sunspots appear, the darker, cooler regions where magnetic field lines break through the surface and prevent convection. Above the photosphere lies the chromosphere, a reddish layer visible to humans only during solar eclipses. Higher still is the transition region, a thin layer where temperatures rise dramatically from thousands to millions of degrees over just a few hundred kilometers. Finally, we reach the corona, the Sun's outer atmosphere. The corona extends millions of miles into space and reaches temperatures over 1 million degrees Fahrenheit, hundreds of times hotter than the surface below it. The temperature inversion defies our intuitive understanding of heat transfer and remains one of solar physics' greatest puzzles. NASA's Parker Solar Probe is currently up there studying the corona and actually made its first pass through it on Christmas Eve last year. Unlike the Sun's inner layers, which are held together by gravity, the corona's high-energy particles are able to escape the Sun's gravitational pull. This leads us to our next topic. The expansion of the corona creates what we call solar wind, a constant stream of charged particles flowing from the Sun in all directions at remarkable speeds. These particles follow curved trajectories following the magnetic field lines. The solar wind consists primarily of electrons and protons ejected from the Sun's upper atmosphere. It travels through space at between 250 and 750 kilometers per second on average. That's roughly 1 to 2 million miles per hour. At this speed, particles can travel from the Sun to Earth in just 2 to 4 days. As the solar wind travels through space, it carries with it the Sun's magnetic field. This creates what we call the interplanetary magnetic field, which fills up our entire solar system. These charged particles can be quite challenging for humans and spacecraft, but are extremely important for protecting the solar system from the interstellar medium. As it pushes outward, it forms a vast magnetic bubble known as the heliosphere, which extends well beyond Pluto and forms the boundary layer between our solar system and interstellar space. The Voyager missions launched in 1977 only recently crossed this threshold, 2012 for Voyager 1 and 2018 for Voyager 2. The solar wind's pressure also shapes the magnetic fields of all of the planets in our solar system, including Earth's. It's constantly bombarding our planet at a rate of about 1 million tons of material per second, which brings us to how our planet responds to this continuous solar onslaught. Hey everyone, if you're enjoying this video, take a second to like and subscribe. Okay, now let's get back to it. Fortunately for life on Earth, our planet has evolved a natural shield against the solar wind, its magnetic field or magnetosphere. Earth's magnetic field originates primarily from its outer core, a rotating sphere of molten iron and nickel about 1,800 miles below our feet. The movement of this electrically conductive fluid generates what scientists call a geodynamo effect, creating a self-sustaining magnetic field. This is similar to how an electrical current flowing through a wire creates a magnetic field around it, except on a planetary scale. When the solar wind encounters Earth's magnetic field, something remarkable happens. The charged particles can't easily cross the magnetic field lines, so most get deflected around our planet. This creates a protective bubble around Earth called the magnetosphere. The magnetosphere isn't symmetrical. On the day side, facing the sun, the solar wind compresses the magnetosphere to about 6 to 10 Earth radii, or approximately 25,000 to 40,000 miles. On the night side, the magnetosphere stretches into a long tail called the magnetotail, extending hundreds of thousands of miles, sometimes even reaching the orbit of the moon. The boundary where the solar wind first interacts with the Earth's magnetic field is called the bow shock, named after the wave that forms in front of a moving ship. Inside the magnetosphere, charged particles from the solar wind become trapped, following magnetic field lines in complex spiraling paths in and around Earth. These trapped particles form structures called the Van Allen radiation belts. The Van Allen radiation belts were one of the first major discoveries of the space age, detected by instruments on America's very first satellite, Explorer 1, in 1958. These belts consist of highly energetic particles trapped in Earth's magnetic field. These belts serve as a protective mechanism for Earth, capturing harmful radiation that would otherwise reach the surface. However, they pose significant challenges for space travel and satellites. The high radiation levels can damage electronic components and pose health risks to astronauts. NASA and other space agencies carefully plan mission trajectories to minimize time spent in the high radiation zones. The International Space Station orbits at about 250 miles above Earth, well below the inner belt. Meanwhile, communication satellites in geosynchronous orbit at 22,000 miles must operate within the outer belt, requiring special radiation hardening to function reliably. While the Van Allen belts provide general protection, Earth's magnetic shield has an interesting weakness worth examining. There's a region called the South Atlantic Anomaly, where the inner Van Allen radiation belt comes unusually close to the Earth's surface. This region stretches over much of South America and the southern Atlantic Ocean, covering parts of Brazil, Argentina, and extending towards southern Africa. This anomaly exists because Earth's magnetic field isn't perfectly aligned with our rotation axis. It's tilted by about 11 degrees and offset from Earth's center by nearly 300 miles. This misalignment creates a weaker magnetic field in the South Atlantic region. In this anomaly, the inner radiation belt dips down to just 120 miles above the Earth's surface, compared to the typical 600 or 1,000 miles elsewhere. This means satellites in low Earth orbit receive increased radiation exposure when passing through this region. The International Space Station, when passing through the South Atlantic Anomaly, experiences radiation levels that are 5 to 10 times higher than in other parts of its orbit. Astronauts report seeing flashes of light when their eyes are closed. These are actually high-energy particles striking their retinas. Space agencies typically schedule crew members to avoid sensitive activities while passing through this region. While the solar wind and its interaction with Earth's magnetic field are fairly constant, the sun occasionally unleashes much more dramatic events. The sun is far from a static object. Its surface and atmosphere are constantly churning with activity, and sometimes this activity leads to explosive events called solar flares or coronal mass ejections, CMEs. First, let's clarify the difference between these two phenomena, as they're often confused. Solar flares are sudden, intense bursts of radiation from the sun's surface. Flares occur when magnetic energy built up in the solar atmosphere is suddenly released. They emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, which can interrupt communication technologies. Coronal mass ejections, or CMEs, often occur along with flares, but are distinct events. A CME is a massive burst of solar wind and magnetic fields rising above the solar corona. They can eject billions of tons of coronal material at speeds ranging from 250 kilometers per second to as fast as 3,000 kilometers per second in extreme cases. They can also disrupt communications, but they can also damage satellites and electrical transmission lines. Both flares and CMEs are powered by the sun's magnetic field. The sun's surface is a tangled web of magnetic field lines. As the sun rotates, these magnetic field lines can become twisted and distorted, like rubber bands being wound up. Eventually, this magnetic tension reaches a breaking point, resulting in magnetic reconnection, where magnetic field lines break and reconnect in a new configuration, releasing enormous amounts of energy. Although most CMEs are not, when a CME is directed at Earth, it can trigger a geomagnetic storm upon impact. The journey from Sun to Earth typically takes 1 to 3 days, giving scientists some time to prepare for potential impacts. NASA and NOAA monitor the Sun continuously using satellites like SOHO and STEREO, providing early warnings for significant solar events. The frequency of solar flares and CMEs follows the Sun's 11-year cycle. During solar maximum, several CMEs might occur per day, while during solar minimum, they might occur only once every few days or weeks. Let's explore what happens when these powerful solar eruptions reach Earth. When a CME, or high-speed solar wind stream, strikes Earth's magnetosphere, it triggers a sequence of events collectively known as a magnetic storm. During a geomagnetic storm, the pressure from the solar wind compresses Earth's magnetosphere on the day side and stretches the magnetotail even further on the night side. This compression causes the magnetic field lines to break and reconnect, allowing solar particles to enter the upper atmosphere near the poles, where field lines converge. This influx of energy and particles affects multiple layers of the Earth's atmosphere. In the ionosphere, a region extending from about 30 to 600 miles above the Earth's surface, the additional energy ionizes gas molecules, temporarily altering the density and composition of this layer. Since the ionosphere reflects and refracts radio waves, these changes can disrupt radio communications, particularly high-frequency radio used in aviation and maritime operations. In the thermosphere, which overlaps with the ionosphere but extends higher, the additional energy causes heating and expansion. This expanded atmosphere creates increased drag on satellites in low Earth orbit, causing them to lose altitude faster than normal. After the severe solar storms of March 1989, some satellites dropped by over half a mile in altitude. The effects aren't limited to the upper atmosphere. Changes in the ionosphere can affect the accuracy of GPS signals by altering the time it takes radio signals to travel through this layer. During severe storms, GPS accuracy can degrade significantly, affecting navigation systems worldwide. Perhaps most seriously, geomagnetic storms induce electrical currents in long conductors on Earth's surface, such as power lines and pipelines. These geomagnetically induced currents can overload electrical transformers. In March 1989, a severe geomagnetic storm collapsed the Hydro-Quebec power grid in Canada in just 90 seconds, leaving 6 million people without power for 9 hours during the winter. But geomagnetic storms also create one of nature's most spectacular displays, auroras. The northern and southern lights are nature's most visible and beautiful manifestations of the Sun-Earth connection. These colorful atmospheric displays occur when charged particles from the solar wind, or CMEs, follow Earth's magnetic field lines towards the magnetic poles. When these high-energy particles collide with atoms and molecules in the upper atmosphere, they transfer energy, causing these atmospheric gases to emit light, similar to how a neon sign works. The colors we see in auroras depend on which atmospheric gases are being excited and at what altitude. Oxygen atoms, when struck by solar particles, emit either green light at lower altitudes or red light at higher altitudes. Nitrogen molecules produce blue or purplish red light. The complex shifting patterns we see are due to constantly changing interactions between the solar wind, Earth's magnetic field, and our atmosphere. Auroras typically form in oval-shaped regions around Earth's magnetic poles, called the auroral ovals. During normal conditions, these ovals hover at around 65 to 70 degrees magnetic latitude, making auroras visible from places like Alaska, northern Canada, Scandinavia, and Antarctica. However, during strong geomagnetic storms, these auroral ovals expand toward the equator. During the extreme Carrington event of 1859, the most powerful geomagnetic storm on record, auroras were visible as far south as Cuba and Hawaii. More recently, during the Halloween storms of 2003, auroras were seen in the Mediterranean countries and southern United States. Beyond their beauty, auroras serve as a visible indicator of space weather conditions. Scientists monitor their intensity and location to track geomagnetic storm strength. Interestingly, Earth isn't the only planet with auroras. Any planet with both an atmosphere and a magnetic field can produce them. Jupiter has the most powerful auroras in our solar system due to its massive magnetic field and interactions with its moons. Saturn, Uranus, and Neptune also display auroras, each with unique characteristics, from their unique magnetic fields and atmospheric composition. The relationship between the Sun and Earth exemplifies the interconnectedness of our solar system, from nuclear fusion reacting at the Sun's core to the delicate dance of charged particles creating auroras in our night sky. We've explored a complex chain of events spanning 93 million miles of space. This cosmic relationship has shaped Earth throughout its history. Our magnetosphere has protected the atmosphere from being stripped away by the solar wind, a fate that befell Mars when it lost its global magnetic field lines billions of years ago. Without this protection, Earth might have become another barren, radiation-bathed world incapable of supporting complex life. Today, as our technological civilization grows increasingly dependent on satellites, power grids, and electronic communications, understanding this Sun-Earth connection has practical importance. Space weather forecasting has become essential for protecting vulnerable infrastructure from solar storms. The next time you see an aurora or simply bask in sunlight, remember, you're experiencing the latest chapter in an ancient cosmic relationship, a dance between Sun and Earth that began over 4 billion years ago and continues every moment of every day. Thanks for joining me on this exploration from the Sun to Earth. If you enjoyed it, please like and subscribe, and let me know in the comments below if there's any topics you'd like me to cover in the future. See you next time.